Okay, I need your consent that I will publish this in YouTube publicly. So if you don't want it, so you just close your face. Okay, so good evening, everyone. Okay, let's start our class today. Okay, let's start with the simple workshop first. Can you see my slide? Okay, so let's do a practice policy using IFN. Okay, so you will create a base scenario and alternative scenario. Okay, simply by copy and paste only. Okay, you can also use the Excel add-ins later. Okay, um, yeah, there is Excel add-ins in the Repole 2, but you also have a better version. In the public one is version 2, I think. The one that you have is already version 7. Okay, so there is also Python if you use on the online is already, I think, yeah, you're already familiar with this. Okay, so now these are several Excel add-ins function. Okay, when you put equal and underscore, it will give you the menu. So these are the important function that you probably want to use. Okay, so you want to check whether they are ideal flow or not. Okay, whether they are strongly connected or not. This is irreducible. Whether they are premagic or not. Yeah. Later we will see that the most ideal one is actually premagic capacity. Yeah. And then if you want to get the stochastic matrix, you can get from the capacity matrix or from the flow matrix. Yeah. So these are the commands or the functions. And then you can also get the flow, ideal flow from the capacity or from the stochastic matrix. Yeah. If you don't put anything, that means the kappa mean the total flow is 1. Okay. Now, then you can also get directly the congestion. Okay. There are several ways to do. One is to calculate using the flow divided by the capacity. But if you use Hadamard division, okay, meaning that 0 divided by 0 still 0. Okay. Now, you can also use directly from capacity to maximum congestion. So this is the capacity matrix that you put, and then these are the scalar maximum congestion, for example, 0.9. Okay. Or you can also use this capacity to congestion, again from capacity, but the difference is this is not congestion, but this is kappa. This is kappa mean the total flow that you set. Okay. And if you want to get the Markov chain of this inside its node, you can also use this, yeah, node vector. Again, from the capacity matrix, you set the kappa mean the total flow, then you will get the Markov chain. Yeah. And then if you want to do scaling, you can do this from the total flow, the kappa, you can go to maximum congestion. And if you want to use it for transportation, you probably want to calculate the speed, minimum uh, travel time and delay. Yeah. So if you want to do it on your own, of course, you don't want to get the average of everything. You only want to get the average of the positive value, right? The 0 is not included. If you put average by using Excel, you will get the average including the 0. So this function and average positive, that means only get the positive value, okay, of the matrix, yeah, or median value of the matrix. Okay, let's practice, okay? First thing first, you have two networks here, left and right. Okay, which one is transportation network? Anyone?
The left, sir.
The left
The
one,
right, the right, the right,
the
the
right
right
one,
one.
okay?
Because
Why the left one is not transportation network?
uh Because if I go because of the CNF link.
Right. So from the left part, A, B, C, okay, you can go to D, E,
Right.
F, but you cannot go home,
Yes,
right?
sir.
So how can you make a transportation? How dare you create a transportation network? Okay, that you can create a way to go somewhere, but you cannot go home, right? So this is not. So uh, transportation network means the network must be strongly connected. Yeah, meaning from any node
Yes,
you
sir.
can go to any other node and come back. Okay, to that node. So now the way I put network, yeah, let's go to the right network here. Okay, so I put capacity as the number of lane. Okay, so when I put like this, capacity as the number of lane. So here, for example, A to D have only one lane. D to E have two lanes. Yeah? E to D have two lanes and so on. Okay, so let's say this is our base scenario, the current. Okay, and then let's improve that through hoping to improve, yeah, through increasing the number of lane in DE. Yeah, so here from two now become three lanes, and the rest are the same. So this is called policy, meaning you add a policy. What is the policy? Adding one lane. Yeah, in this case, in link DE. So now become three here. Okay, so for your practice, today we'll do practice, yeah. So first you compute the stochastic matrix, yeah, from the capacity matrix, yeah. And then you compute the ideal flow matrix from the stochastic matrix, and then you compute the congestion from the ideal flow, yeah. And then you can calculate the speed, travel time, and delay. So this is like very basic. Okay, we need to be able to do this, yeah. So let's set up the parameter. Okay, uh, the capacity per lane, let's set up as 1,800 PCU per hour. Okay, a simplified version. So we will do maximum speed is 40 kilometer per hour. Okay, and then just simplify again. So all the link length is 1 kilometer. Okay, suppose you know, okay, uh, three things. Yeah. Now we will calibrate this ideal flow network with three type of calibration. Yeah. Number one is if you know the total demand. Okay. Number two, if you don't know the total demand, but you know the maximum congestion, 0.9. Or you don't know the total demand, you don't know the maximum congestion, but you know the real link that you survey in link DE was 3,000 PCU per hour. This is based on the real survey. So either one. Okay, let's do this. So what you will do is you create a matrix like this. Okay, capacity matrix. Because our capacity per lane is 1,800 PCU per hour. Okay, so what we will do? We multiply this, right? So if one lane then become 1,800. If you have two lanes, that means 2 times 1,800 become 3,600 PCU per hour. Yeah. So this is capacity matrix in number of lane per direction. Okay. In here on the right side here is the capacity matrix, okay, in PCU per hour per direction. Yeah. Up to here, is it clear? Eh? So you have the network. Yeah, this is the network, and then you can set it into PCU per hour per direction. Yeah, this is the capacity. Capacity mean maximum flow. Okay. Okay. So say you have this node table. Okay. All you need to do is just copy and paste. Okay. Not including the label, only this part. And then the link table also you can copy and paste. Yeah, let's do that. I will demonstrate. Okay, let's go to IFN Transport. Yeah, now it's official in the main part. So you can go to network. Okay, so I just select any. Okay, say actually maybe I have it already here. Okay, maybe this one. Yeah. Or we can use this one. Let's copy and paste. Okay, the node. Control C. Go back to this. Okay, and in the node you just oh sorry, I need to copy again. Control C. Okay, and then here you paste it, right? In here I clean and then I copy from the link table. Yeah, not including the um, label, yeah, only the numbers. Okay, you can also do the
Quick
same.
question.
Yes.
Why is it two block quickly connected? The network example.
No, no. You can uh,
We just ignore this.
ignore this. Ignore this.
Okay, okay.
Okay. Uh, once you have this node matrix and link matrix, you can download this. Okay. So you can name it. Okay. Network example. What is this? Base scenario. Okay. And then, okay, before we download, let's check this. Let's do it 250. Okay, you can zoom. Is that correct? The one that you want? Oh yeah, correct. It come back. Okay, right? And then the first problem is here. I have a total demand of 17,500. Okay, so what we will do with that? Okay, so in this case, you go to ideal flow here. Okay, you have total flow of 17,500. Right. So the PPR, I just do the same number of lanes. Uh, Let me check. In here is already 1,800. That means it's already in PCU per hour, right? So in that case, okay, we have a network that we just put a while ago, just copy and paste, right? So I just change the name, description, and then this is the network itself. You can see here, right? And then what we will do is we set the model, ideal flow network, total flow 17,500, and then still PPR, and then capacity is 1 because we are already in PCU per hour. Okay. And then what you will do, you calculate. Yeah. See, total flow is 17,500. So you get that. Yeah. Where is the maximum speed congestion is 8, 9. You can check in here. There. Okay. This is the maximum congestion is here. Okay, let me make it larger so that you can see. 8, 9, 555. Yeah. So this is the first part. Okay, and then what you will do is you save this. Yeah. There. Okay, so now it's your turn. Okay, can you get this? Same thing? Or you have any problem? Once you have that, we can go to the second one. What happens if we make the total flow is 0.9? Okay, so if you want to make the total flow 0.9, what you will do, just go here. Okay, you just change, sorry, the maximum congestion, yeah, maximum congestion 0.9. Okay, all you do, and then change that. Okay, the total flow will change. Okay, now the maximum congestion is 90%. And then for the third problem, okay, if you know the link in DE is 3000 PCU per hour, what you will do? Go here. Now you have the real world. Link DE. DE is 4 to 5. Right? So you put 4,5, 3000, and then semicolon, and then calculate. There. Now the total flow change. The flow in here exactly, yeah, 3000. So automatically calibrated. So up to here, is there any question you want to share your screen that you can to recite probably? So if you know the actual result from the calibration, from the data, say you do a traffic count, okay, and then you input that into real flow, okay. So, and then IFN will calibrate for you. Then you will see here exactly 3000. Yeah, almost. No, not exact, but almost.
Sir, I have a question because,
Mhm.
like, isn't it that I use 3,000 for 4 and 5? How come it's still 1818 here, but the result for link 7 is the one that changed?
1.8 is the capacity, right?
That's not the PCU.
That is the one that you put in the data. Go
Yes, sir,
back
the
to
one.
the data.
Yeah,
This three, this link number, start node, end node, capacity, distance, max speed are from the data. They don't change.
okay. So when I change it like 4 comma 5 3000, even if it's link 4 and 5, I'm actually talking about link 7 and 6. This
Yeah,
is very
because
evident.
that one is 4 and 5 is the start node and end node.
Oh, okay. So I do not expect to see it here in 4 and 5, but it's actually here in 6 and 7 that is nearing that
6 and
3,000.
7.
This is the ID, sir, diba? Because
Yeah.
the 3,000 flow I
Okay.
have
Let's
is
come back to your
7.
data, your model, so that you will see.
Okay, sir.
See, this one is node 1 and then node 2 and then actual flow.
Yes, sir.
Okay, and then you go to the
This is the
network
one I
data.
changed.
Yeah, this is the one that you changed. Go back to the network tab. And
This is
then
not.
yes, and then look at the that one. Here, link 7 in the link matrix, can you see? Link 7
Yes.
is from node 4.
Oh, to node 5.
Yeah.
Okay. I got confused between the link and the node because
Yes.
I was
So,
thinking, okay. So the node is 4 and 5, but I'm actually talking about the link
yes.
7.
Right.
Thank you. Thank you, sir.
Right. Okay, good. Okay. Yes, Sophia, you want to say something?
Sir, just want to I'll share my screen.
Smaller, maybe 250, maybe. Okay, 500. So why this is weakly connected? Can you improve so that it will become strongly connected?
This one, sir. Can I?
Yes, you can change that. So this one is C to F. So let's go up to the link matrix. So let's change that C to F. Where is that? C to maybe down. I think down maybe. Maybe link. Oh, there. Now you change that to F to C. Okay, and then going down, check. Okay. Now you can see how you change in the link matrix, can see the change in the network and check whether they are strongly connected. Oh, test. Is it?
Up appeared this the network is strongly connected. You
Okay.
cannot see.
Yes. Yes. Very good. So now once the model is already strongly connected, you go to the model tab.
There.
Okay. And a while ago, what is the capacity? I forgot. Sorry, can you come back to the network tab? What is the link matrix capacity? It's in the number of lane here, right? 1, 2, 3, 4, right? So in that case, in their model, you need to change it into PCU. Okay, let's see the capacity matrix. Okay, it's already PCU, 1,800. Okay, you can change that, become 1,500 or whatever number that you can set based on the highway capacity manual. Okay, and then you can go to the result tab and calculate. Yes. Okay. Oh,
This one. Multiplier.
the multiplier is
It's a valid input in capacity multiplier.
yes, because you are setting
One. I think it should.
you're supposed to set as lane per number of lane, right? Correct. And then that one now become 1,800, the multiplier. Okay. Now you go to calculate. There. You got it.
Yes, sir. But in here, sir, for example, I want to
Change to
change
real flow.
maximum flow, total
Okay.
flow. This part or real flow.
Okay.
This input that may change. It's still maximum congestion level.
Wait, really?
Yeah, that was the main problem, sir. Even if I change
Okay.
the parameters.
I think this is thank you for this input. So I think this is the browser problem. Can we use Chrome?
Okay. I don't have right now, sir, but I'll just try it.
Yes. So
I'll
this probably browser problem. No? Can you use Google Chrome probably?
I can try.
Mm-hmm. There, Google.
Mm, Google.
Yeah, you have Google already there.
Okay.
In your favorite a while ago, you have already Google. Okay. Go to. Is this using Google already?
No, sir, this is Safari.
Oh, still Safari.
I don't have it now.
Okay. Yeah. I did not test using Safari yet, so I don't know why it's not working in Safari. It's supposed to be okay now because it's pure HTML, supposed to be okay. Anyway, okay. So try to use Chrome. Okay. I hope this will help you. Anyone have other problem or similar?
Actually, Prof, I have the same concern because I'm using Safari as well.
Okay, so okay, thank you that this is not working in Safari. I will try to test it in Safari in that case. Yeah, it's my fault. Okay, I did not test it in Safari, but I'm sure in Google Chrome it works. You can try download Google Chrome. Okay, so let's try it in Excel. Okay, the same thing. Can you see my screen? Okay, so the same thing now, we want to do it in Excel. So what to do? Well, what we will do is just create a matrix. Okay, in Excel, we do it in matrix form. Okay, so I will type here A, B, C, D, E. Okay, here A, B, C, D, E, right? And then I'm supposed to have one in here, and then one here, one. Is that correct? E. Oh, until F, sorry. So until F, we have six. Yeah. One here. And then here we have two. And then here we have D to E have two. And then here two and here two. Here have one and one. Is that correct? So I put this yellow, okay, on the right side. If you want become neat, you can just format it along with, for example, you make it 3. Okay, so we have capacity matrix. Okay, we just type this, okay, based on the slide, right? So the same capacity, okay, when you put it here, we can make one piece, one lane is actually, so capacity per lane is say 1,800. Yeah, PCU per hour, right? So we do it manually here. So what you will do? So I will just type here multiplier. Um, did I record this? Yes, okay. Okay, so this is name multiplier. This one, right? And then let me make it yellow. And from here, we just multiply the multiplier with the capacity, yeah. So that we will get capacity matrix in PCU per hour per direction. Yeah. Is it the same? Okay. 3,600, 3,600. This one. Yes, I think this is the same, yeah. So once you have the capacity matrix, okay, you want to calculate the stochastic matrix, okay. So all you need to do is just n underscore, right? So capacity C to stochastic matrix, yeah. So this is the stochastic matrix. Okay, close it, and then you highlight 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 here like this, and then you click here, and then press Shift and Control and Enter together. Yeah. Yeah. Okay, so you get the stochastic matrix. Let me color it differently. How do you know that this is stochastic? You can get the sum. Yeah, the sum must be 1. If it is stochastic matrix, yeah, the sum in each row must be 1. So this is the sign of stochastic matrix. Yeah, and here we can get the ideal flow matrix. Okay, so we'll just copy here also, and then copy the name of the label of the node. Right. So copy that later we will have it here. This is for G. Okay, so for the ideal flow matrix, you just put n underscore. So where you want to get? You want to get it from the stochastic matrix or from the capacity matrix. So to get the flow, okay, you need to get the total flow. So this is the total flow. Okay, so I will put temporarily 1. Okay, so I will put temporarily 1. This one again, PCU problem. So let me call this kappa, okay? Kappa. There. And you see, I rename it here, okay, in this box as kappa. Okay. Then what I will do, I will put here n underscore. Okay, let's do it from stochastic. Yeah, stochastic to ideal flow. There. Where is the stochastic matrix? This one, right? And then you need to put the kappa. Okay, and then you close it, enter, then you highlight all this, yeah. You select all, and then Shift Control. You go here first, edit, Shift Control, enter. Oh, there. Yeah, very small. And with this, we can change this to 100. Why? And 1000. Now let me check if this is maybe my computation is my data is maybe not correct. Okay, let me check is strongly connected or not. Yeah, strongly connected. So here n underscore is irreducible of this one. Oh, false. That's why. Okay, if it is not irreducible, okay, the value is incorrect. You see, what is wrong here? If you want to see, okay, you go here, I copy this, the node, okay, and then I can put X and Y. Okay, let me draw any value. Say I will put in here 100. Okay, I just copy this. Okay, this one also copy. This one is like this one plus 100. Okay, and then I copy again, and I copy again. Okay, so let me put this one is 50. Say 100 again in here. So 200 and 300. And then I copy exact the same. So that I will see the coordinate, okay? Then I will draw the network. Okay, so underscore and underscore draw network. Okay, so let me draw the capacity matrix and the coordinate. There. Okay, if you don't like in 100, you can change that to 500 maybe. It will move. Okay, maybe 700. There. Or maybe 900. Still too much. I will make it 1000. There. Okay, this is the network going there, going there. Oh, why? Why this is not strongly connected? It should be strong. Oh, this one. This one is D to D. This is supposed to be D to E. Okay, that's why it's a mistake. Oh, there. It's a mistake a while ago. Ah, you see when we correct it, it comes strongly connected. The base capacity, yes. Okay. Now I corrected. Okay, thank you.
Sir, the
ENF are still in.
F2E, sir.
F
I think the value of the F2, it should, the
F2E.
number one value should be on the F2E
F to E. Ah, okay. This one also
instead of
wrong.
F2D. Yes,
Okay.
and then
Okay.
also
This one is
the E to D. E to D should be 2.
E to
Then
D.
there's no value. Yes, there's no
Okay.
value on E to C.
This one. Okay.
And then the value for F to C should be 1. And then
F
0 for F to C 1. And then no value for F to B.
now is
Yeah,
it
there. Yes, sir.
correct? Okay. So now we are the same.
Yes, sir. You're the
Right.
same.
Very good. Now you can see when we put the sum of all, right? The sum of all of this must be exactly the same as the total flow, right? Oh, yes. So we get the result is exactly the same. Okay, I will color it. Maybe green. Okay, so whatever you change in here, the parameter that you put, of course, this is exactly what you will get. Right. Okay. Next, what you will do, you will get the capacity. Yeah, you want to get the capacity matrix here. So just copy this. So capacity is just flow divided by the capacity. No, congestion, sorry. You want to get the congestion, right? So congestion is just flow divided by capacity. So in here, you will get N underscore Hadamard division. It's Hadamard division of the flow, comma, the capacity. Yeah. Close it. Okay. And then again, you do the same thing. Yeah. Okay, so here and then shift, yeah, you highlight, okay, and then edit and then shift control enter. There you get the congestion level. For congestion, what you will get is actually the maximum congestion, yeah, maximum congestion. Okay, so I will put here max of this value. Oh, 0.1 only. Okay, 0.1. Okay, so this is not what we want, right? Okay, what we want maximum congestion should be 0.9 or 0.8 probably. Okay, so in that case, what you will do, you change this. Okay, then what happens if I change it to 17,500? Okay, oh, it's almost, huh? But this is not yet. So in that case, you can use one way is to use sulfur, right? So you can use sulfur. What you will do, you go to this value of maximum congestion, which is in my case R40, and then check here. I want it to become 0.9. What I will change, I want to change my parameter of total flow. Oh well, I have a problem with my Excel. Oh, there. Apparently the Zoom and the Excel is interfering. Okay, by changing this L4, in this case total flow, the parameter, then I put solve. Almost. So click OK. Now I get exactly 0.9. Okay, almost. And this is the total flow that you're supposed to get. Okay. Let's review what we just did. Okay. You have a capacity and you have a network basically, yeah. And then you set it into network in PCU per hour. Okay. You calculate the turning distribution, right? This one is mean in each node, in each intersection, what is the probability to turn left and right and straight, right? This is the value. And then you can get the actual flow for each link, right? And then you can get the actual congestion level in each link. And then you can calibrate that congestion level. Okay, how do you calibrate? Because we have one parameter here, which is the total flow. Okay, so this is what you will get. Yeah? The same thing. So say a while ago you said, okay, I want to get 3,000 in link DE, this one. right now is 3,400, 200. You don't like that 3,200, right? The one that you get from the real data is 3,000. So what you will do, you solve for, this is the one. DE is 0.27. So I will go here. Link DE, I put here, 0.27. What is the value? I want to make it 3,000. Yeah, again, keep the changing the cell of kappa. I got the sol. You see, exactly 3,000 and the kappa change. Do you get the idea now?
Yes, sir.
Okay. So when you change the value in your based on real data or based on your assumption here, 0.9, okay, all you need to do is to change the internal parameter inside the IFN, which is the total flow. Okay. Now you get new data, right? Say, for example, oh, I want to change this. Okay, so I copy the whole sheet, okay, here and create copy. Okay, I have a new data here. Now suppose what? The new one is in DE now become 3 lanes. In sheet 2, now I change this, now become 3 lane. Then, okay, now become 3 lanes. So I will put this in bold so that you will know this is actually the one that I changed, right? Compared to earlier, this is 2 lane. Okay. In sheet 2, now we have 3 lanes here. Because 3 lanes, so of course now become 5,400. Okay. And to calibrate, okay, you see, I have this total flow, and then I have also here now become 3 lane. What will happen? Now, of course, the congestion level reduce. Yeah. Earlier was 0.8, which is congested. Now become 3 lane, now become 0.7. Okay. So your congestion level reduced. That means your alternative solution. So this is the seed one a while ago, we call it base, right? And then the seed two, now we name it as alternative, right? So the alternative solution is actually better than the base, yeah? Yeah. Why? Because this one is now 0.7 a while ago, in the base is 0.8, right? So up to here, is there any question? Is it clear or not? Yeah, this is the one that we just did. Yeah, of course, when you want to check whether this ideal flow is pre-magic or not, you can check, yeah. You can share the screen. Here you can just take the sum, right? So the sum in this uh, row and compare it to the sum in the column. The copy. Oh, you see, this is exactly pre-magic, yeah. 857. Here is also 857. 2571, 2571, 2142. This one is 2142. This is exactly 1000. Okay, and then again the same, yeah, exactly the same. So this is pretty much it. In fact, you can also check here. N underscore is pre-magic. Yeah. You can check here, is pre-magic or not. I hope this is correct. Oh yeah, it's true. Yeah. So easy. I hope this is clearer. So you can do using Excel, you can do using the online one. The only difference is the online one, the formatting of the link and notes, yeah, right. In Excel, you need to use in matrix form. Yeah. So, anyone want to share screen or have any question probably?
Sir,
No?
I just have a question on how to draw the network.
Okay.
I do that.
Okay. To draw the
Okay,
net.
can I share my screen, sir?
Sure. Go.
I'm just having trouble with the drawing. Can you see? Can you see my screen?
Not yet. Oh, there. Yeah. Okay. So, okay. So
Okay.
you use this, no problem. So N underscore
Okay.
D.
Draw network.
Yes, draw network.
And
And then
then
go to the matrix from C4, your capacity matrix, right?
this one.
Yes. Until it's sorry, comma, and then
Oh,
your
okay.
L4,
And
L,
then this one.
yeah, the
L.
port L, yeah,
Ah, and
yes, okay.
then close.
And then close, yes,
Okay. Because
and
I only said this one
yes,
earlier.
and
That's
press
why it's
enter. It's supposed to be there. Is it?
other. Here, sir.
Okay, there. Okay, so you can change that 1,200 become 900 probably so that you can see in the same
Okay,
place.
sir. Oh, that's only my questions. I
Yes.
already have that.
And now if you want to delete, that is the next problem.
How do you delete this one, sir?
Okay, so if you want to delete this, you delete that draw network.
Okay. Delete as in delete.
Yes, delete that one. So and then you put again n equal n underscore I think delete shape
Delete?
or shape delete or no
Okay. If
underscore n
under
underscore shape delete or delete shape, I forgot. Either shape delete or delete shape.
it's not working, sir.
It's not working. Go. Uh, in the documentation, I think there is. Delete shape. N
Delete
underscore delete shape.
and underscore delete.
Delete
Delete
shape.
shape.
Yeah, delete shape.
And then
Yeah, and then it's deleted, right? And then you can just delete that delete shape.
what value should I put here, sir?
Nothing. You
Just
just
enter this
open
one.
and close it. Open and close only.
Okay, it deleted already
It- it-
the shape.
Then you can delete that.
Okay, sir. Thank you. Thank
Sir,
you, sir.
I have
Yes,
additional question. Like
yes.
in what Tracy just did, that we have to draw the network. We always have to make an X, Y, and then we just assume numbers there. Can't we
Hmm.
do draw network based on the ABCD, the matrix by itself?
I think it's the same as the node matrix in the website, isn't it? But
Yeah, I mean,
the value is not the because in Excel you have limited value. So
yes.
the zero and so on is based on Excel. So we cannot scale it.
So it's like, for example, there are two of us doing the same problem, and then if we assume, will we still get this using Excel? Will we still get the same? I mean, we have the same matrix, but we both have different random numbers using in drawing the network. Will we still
No
arrive at the
problem.
same?
Yeah. So remember your linkage, the link matrix in the website, okay,
Mm-hmm,
it's the same as your capacity matrix in
mm-hmm.
Excel. That is the interconnection between nodes. Okay.
Okay.
While to draw the network, you just add exactly the same node.
Okay. But
Okay.
you assume the value, sir, right? The
Now you
one.
need to scale the value
Oh.
based on Excel. Otherwise, you will get the drawing, but very far down there. You
Okay.
cannot even see where.
Oh, so it's just scaling, sir. So like for example, in the class, there's 13 of us, and then we assume different values of scaling.
No
We'll still get
problem.
the
Yeah.
same drawing. Okay.
Yes. The same
Okay.
drawing, but different scale. No problem.
Okay.
Remember, drawing is just visualization so that you can see it well.
Okay.
Okay. It
Ah,
will not affect any computation.
okay. Thank you, sir.
Great. Yeah. So anyone else have question? Now, your challenge. Okay. Your challenge is this. Okay. Um, so I will go to the next slide, which is in congestion redistribution. Let me get into. Okay, let me get into this screen first. Okay, so you get the congestion matrix, yeah, which is simply ideal flow divided by the capacity, right? The only problem is you need to put it in the same unit, yeah, because flow must be in PCU per hour, and then capacity must be in the same unit, which is PCU per hour. Remember, VC ratio is unitless, yeah? No unit. Okay. So then your challenge is to check, okay, the average travel time, the speed and delay, okay, as the basis of comparison for the base scenario and then for the alternative scenario. Yeah. So again, the results are all in matrix form. Yeah. If you use it in the website, this is already in the result table like this. Yeah. The same thing. Yeah. Okay. So with this, is there any question? No question at all?
No more, sir.
Good. So let's do let me get the editing on, and then I just updated this one recently. So the congestion redistribution. So let me edit this and then get it to you. So let's go to the policy analysis. Okay. And what you will do is, what you can do with the tools that we have, right? Okay. Can you go to this policy analysis in Moodle? Here, congestion redistribution. So I will close this slide and open the new slide with this redistribution. Can you see it? Okay. So these are the example of scenario that you can do. Okay. So you can add lane, you can reduce lane, yeah, either temporarily or permanently. Yeah, you can change the road width, or yeah, either add or reduce. Okay, or you can add new links. Yeah, add road or remove the road, either permanently or temporarily, or you can change the direction. Yeah. These are the application of scenario, okay, that you can use for this IFN transport. Yeah. Also the traditional traffic assignment. Yeah. Exactly the same scenario. Okay. Now, this is the traditional idea. Okay. You have the demand that would control the amount of supply, isn't it? So when you said, oh, there is a traffic congestion here in Cubao, right? And then you said, oh, the road is congested. So in that case, we need to add more supply. So the demand will control the supply. Okay? When the road is congested, you want to increase the road width to cope with the demand, right? So yes, you can improve using bus lane and so on, increase the number of high occupancy vehicles. But at the same time, at certain times, you will say, okay, I need to expand the road again. Okay, so the policy that you are doing using this traditional idea is we can only add supply, okay, or control the demand, right? But the problem is actually our economy is increasing, our population is also increasing, right? So now I have a new idea in that case, okay? How about if we, instead of, increasing the supply by adding the lane, okay? How about if we rebalance the congestion? How if we rebalance the congestion, yeah? So what is that? Yes, the demand may control the supply, okay, as earlier. That is, put that as past wisdom, okay? That means we already built the road, okay, up to certain lane, certain width, okay, because of the past demand, isn't it? Okay, and when we build that road, when we build that number of lane, it is based on certain wisdom that we cope of that demand at that time. Okay, so Now, the new idea is simple. What if, okay, it is the supply that actually control the demand? We reverse the idea. Okay, that means the supply can be corrected, maybe by reducing at certain place, okay, to make the demand will change to cope with the supply. Do you get the idea or not? Okay. You want to change the supply, number of lane you reduce, okay, in order to make congestion. Okay. Hey, if you reduce the number of lane, is it actually better or not? Right? That's the main question here, right? Most of the traditional thinker will say, no, it's not possible. How can? It's already congested and then you reduce the number of lanes, it will become more congested. Okay. Let's try that idea. Okay. We have the tool to simulate this, right? So why don't we try? Instead of doing it in the real world, we can try it in the computer first, right? That's exactly what's the tool for, right? So the basic idea is you have the correction of the supply, okay, that will create a new equilibrium to balance the congestion of the entire network. Okay, so that means now the balance, the demands can be rebalanced via by the supply chains. Okay, so here is the basic idea. Okay, so I want to redistribute the congestion, meaning the road that is not congested, I want to make it congested. The road that is already congested can reduce. Okay, right now it's imbalance. Okay, there are certain road that is almost empty. The other road is actually very high. Okay, if we rebalance, then the road that is actually not congested now become more congested. The one that congested become less congested. That's the meaning of congestion redistribution. Okay, so you have, let's define it. Yeah? You have a current network N1, and then you have a policy P, okay, and then you create a new network N2, which is basically the same as N1 plus P equal to N2. Okay, you have the base network currently, yeah, and then you have a policy. I don't know what policy you want to put. Okay, a while ago I have a table that these are the example of policy that you can, yeah, our combination of that. Okay, and then based on that policy, you can create alternative scenario, right? N2. Okay, and then from here you calculate the current network, you have the congestion G1, okay, and then the alternative network you have congestion G2, right? So we will say congestion is redistributed if the maximum congestion in G2 is actually less than the maximum congestion in G1. Okay, this is the idea. We just actually did a while ago, but I want you to understand the meaning. So what happened is the maximum congestion in G2, the alternative scenario, must be less than, okay, the congestion in G1. Yeah, this is actually our idea is to create so that the average, yeah, comparing to the maximum, the gap between the average and the maximum congestion is smaller. Okay, so we want the maximum congestion to be smaller. Okay, that's exactly the same as I introduce a new index here. I call it FAR-P index, yeah, which is closer to 1. And then the relative entropy, you can also calculate using relative entropy or entropy ratio. In Excel, you already have that. Yeah? So FAR-P index is simple. Okay, you have the maximum congestion, and then you have the average congestion. Okay, I minus this, and then I divide by the max. Okay, and then I have 1 minus this value. So I call this FAR-P index. Okay, G is the congestion matrix. Okay. So what happened if maximum G is equal exactly with the average G, then this is 0, and then var P will become 1. Okay. It will happen if the congestion is actually uniformly distributed. Yeah, the congestion matrix. Okay. So if you don't want to use var P index, you can also use relative entropy. So relative entropy, okay, in data science or in artificial intelligence, this is very well known. Yeah, this is called the name is Kullback-Leibler divergence, yeah, or KL distance. Okay. Basically, you have that probability, okay, and then you divide with the other probability, okay, and then you take the ln, okay, and then you multiply with the same probability on the numerator here, and then you take the sum, double sum, yeah. So you don't worry how to compute. The IFN Excel add-ins already have this, yeah. So you can just check n underscore relative entropy, you will get that. Okay, so and this is asymmetric distance. That means distance between P and Q is not the same as Q to P. Yeah? And then this is also invariant to scaling. Yeah, you can also use this. So if you look at this between the var P index and the relative entropy, they are almost linear. Yeah? Almost linear. That means you can exchange between relative entropy and var P index. Yeah? But for entropy ratio, they are not linear. So you probably have different meaning of that. Yeah. Okay, let's compare. Okay. In our traditional method, okay, our way of thinking is to reduce the average travel time, isn't it? Using wardrobe principle. Yeah. So you want to reduce the average travel time, and then you want to reduce the average network delay or reduce the network speed, right? That's the traditional way to do. Yeah. Okay. Now, if you use the new concept of congestion redistribution, no, you don't care about the travel time, network delay. What you want is to reduce the maximum congestion. Okay. Maximum congestion is a network performance, you know. Yes, it is in one link, okay, but this is a network performance. You cannot get the maximum unless you compute for the whole network. Okay. And why this is better than, say, average travel time or network delay and so on. Because if you use maximum congestion, you will know which link. You will know the location and the value. If you only use this network delay, speed, and travel time, you know the value, but you don't know the location. That make the problem. Okay. In maximum congestion, you will know where is the location, which link, okay, and what is the value. Of course, the maximum congestion itself, right? And then you can use more efficiently of the road network because you distribute it to the smaller road. This is the idea, okay? And then because of this, you can also reduce the concentration of air pollution, okay? And you can actually reduce, you can justify to reduce the number of lanes, in certain place, okay? Not all, in certain place. Okay, once you do that, you can narrowing the road, okay, and then you can use that road into pedestrian only zone or into green place, no? Okay, so this is much better than the traditional thinking. Yeah? So again, we want to improve the efficiency of the use of the road network. Okay, but of course there are some cons of congestion redistribution. Yeah, so it may increase be careful when you do this. Yeah, it may increase the average travel time, it may increase the average network delay, and then it may decrease the network speed. And then some people may angry, especially in the residential area, because you distribute the traffic to the minor road. Okay, so these are the cons. Okay, so in that case, you can use only primary and secondary up to tertiary road. Yeah, you remove the possibility to enter the residential road. That is the one that you can solve. Yeah, this one. Now, how to do that? How to do rebalancing the congestion? Okay, so now you have base scenario. Let's call this capacity matrix C base. Okay, C is capacity, B in here is a base. So this is the current situation. Okay, what you will do, you compute from the capacity matrix, you can calculate the flow already, right? Remember, we just practiced a while ago. Okay, and then you set the kappa, the total flow is 1. By setting the total flow is 1, you get the probability. Okay, so this is basically the probability. Yeah, and then the probability of the link. Yeah? And then you from here you can calculate the congestion matrix. Yeah, G0. Yeah, the maximum of this, let's call this small G0. And then you have the criterion you are given. For example, the maximum congestion that you want is G1. For example, 0.8 or 0.9. Okay, and this is the formula. Okay, now you want to get the global scaling factor. Yeah, K1, which is equal to K0, which is 1. Okay, equal multiplied by G1, this is given. And then G0, you get it from here, from the congestion matrix where total flow is 1. Okay, from here you get K1. Yeah, this is the total flow. Okay, that is based on global scaling factor. Okay, and then you input this. Yeah, using this CB. Okay, you get the new ideal flow network. Yeah, I call it F1. Okay, which is based on the CP and K1. Okay, from here you get the maximum congestion, which is G1 exactly. Yeah, should be right. And then what you will do, okay, you set this K1 as your invariant for all the scenarios. Yeah, remember in any modeling, if you want to predict, you need to set invariant. Okay, so once you set this as invariant, then you create alternative scenario, yeah, with the CA. Okay, for example, a while ago you add with number of lane or you reduce the number of lane, yeah, based on the policy. Okay, now you have CA, right? And you have K1 as your invariance, then you can compute the flow. Okay, because you have the flow and you have the capacity, you can calculate the congestion, right? Because you know the congestion, you can get the maximum congestion. Okay. Now, what is the expectation? Of course, the expectation is the maximum congestion of the alternative scenario must be less than the target maximum congestion. Yeah. So if your alternative must be less than the given. For example, your given is 0.9, then this one must be 0.7 or 0.8. Okay. So now I want to debunk the myth. Okay. The myth is this. You solve traffic congestion by adding lane. Okay. Why is this a myth? Okay. Because by improving the congestion, by adding lane, you may make worse the congestion in other link. Okay. Yes, in this link, because you increase the number of lane, Okay, it will reduce the congestion in that particular link, but it will make worse in other place, not necessarily better. Yeah. So now the second reason is traffic congestion is actually non-linear. Yeah, non-linear. So here is the graph between the travel time and the congestion. Yeah. So remember the capacity is 1, right? So suppose you can see when the VC ratio or the congestion is actually below 0.8, they are linear. Okay, almost linear. Above 0.8, they are becoming non-linear. Can you see that? Okay, the severity of the travel time and delay, okay, will happen above 0.75 or 0.8. So in that case, we can prove this is a myth by reducing the number of lane to improve the congestion. Is it possible? Let's try. Okay. So again, I have a numerical example here. You need to try after this. Okay. So this is it already in capacity matrix. All you need to do is copy and paste this. Okay. And then, so two things are given. The base scenario and maximum congestion, 0.9. And then you have a policy. Okay. So 3. The base scenario, the maximum congestion, and then the policy. Say, I want to reduce the lane DE here from 4 to become 2. Okay. Okay, of course, you need to get the alternative scenario after that policy, okay, CA. What is CA is exactly this. Now this one become 2. Okay. After that, you compute the flow and the congestion, yeah, and then the scaling factor. Okay. And finally, you will get the CA must be less than your maximum congestion earlier, which is 0.9. Okay. So here is the answer. Okay. So when you reduce the number of lane DE from 4 minus 2, okay, I reduce the number of lane from 4 to 2, okay? And then we compute that. In the base scenario for lane here, I compute the flow matrix for the total flow equal 1. So basically this is probability. Yeah, that sum of this, all of this is 1. Right? So in Excel, I put it this way. So this is the CB, mean the capacity of the base, right? And then I put total flow 1 here, and then you just N underscore capacity to ideal flow. Yeah? And then this one is again the same as earlier. You do Hadamard division between the flow and the capacity matrix. Yeah. Okay. Here is number of lane. I did not put it into PCU value. Okay. Just make it as lane only. So can you see here the maximum congestion is 0.2. Okay. But our target maximum congestion is 0.9, right? In that case, we get the global scaling factor to make it 0.9. Okay. So your target kappa is 0.9. Okay. In that case, kappa is the same as your target, see O20 here, divided by O18. Yeah. O18 is the maximum congestion from this G. Yeah. So 1 multiplied by 0.9 divided by 0.29. So you get 4 point something. Yeah. If you don't like this simple computation, you can use solver. A while ago, I used solver, right? So instead of using solver, we can calculate directly, easily. Yeah. More precise than the solver. Okay. And then once you get that, okay, using this same kappa one, okay, now you create alternative capacity matrix. You see here, I changed to value 2 instead of 4. We reduce the number of lanes. And then we use this new F1A, which is based on kappa 1. Yeah? So the total is the same as kappa 1. And then what we will do, we do congestion matrix, yeah, of this one, yeah, which is 0.83. Yeah. So you see here, earlier we have 0.9, now we improve, become 0.83. Yeah. So can you see that we are actually improving? Yeah? We are improving the network performance, which is based on maximum congestion, around 7%, right? And if you compare the congestion matrix, yeah, this one and this one, yeah, earlier was 0.2, now increase becomes 0.8. So earlier was 0.08, 0.01, now becomes 0.08. So there are increase of congestion level, okay, because we redistributed, yeah, the congestion level. And then from here you can calculate also the FARP index. Yeah, the FARP index, interestingly, you don't even need to compute everything else. Yeah, all you need to do is to get the capacity matrix, and then you can get the FARP index. Yeah, when the FARP index of the alternative scenario is actually better than the base scenario, you will see improve. Yeah? So here, okay, you can see that we compare base and alternative scenario using IFN. You don't even need to use real world data. In fact, I don't even translate it to PCU per hour. Can you see that? Huh? And the policy of adding lane is not always improved, okay? Depending on the traffic situation, the network situation. Lane reduction may also improve the traffic congestion situation. Okay, so and I propose FARP index or maximum congestion to be probably better network performance than the average speed and average travel time. Okay, okay, so any question, any uh, objection? Probably no problem. Okay, any discussion?
Short question.
Go.
I do appreciate that IFN does not need the real world data because that tends to be really very expensive. Like we need to do surveys or pay the DPWH to count the local traffic to do it. But have you ever presented this to like actual scenarios for governments aside from the Ateneo one that you did?
You
Local
well,
governments accept.
that should be your job.
Okay.
Okay,
But
you are in the government, so you have the real data and you have the work in the government, so should be your job to do. As a researcher, we have the limited access to that. Okay,
yes,
so
sir.
our job is to create the theory, to create the software, probably the tools. Okay,
Yes, sir.
but at the same time, you are the practitioner. Okay, so or the consultant should be the one who do that job, right?
Okay, sir. Right. Right.
Mm.
I was just wondering, like, if you have any feedback on how receptive local governments are to this model because they are used to the traditional method.
I understand, but at the same time, the local government already bombarded with the traditional way of
Yeah.
thinking.
Uh-huh.
Okay,
Yes, sir.
so this take time to educate.
Okay.
Okay, so this kind of education is important. Okay, first uh, to you. Okay, uh, I need to convince you first, right? That's
Sure.
number one, right? So if you are not convinced, you cannot convince the other. So you need to convince yourself that this is true and the theory is correct. Okay. and then the simulation is correct, you can check by yourself. Okay, in the small network like in Athenian network, it works, right? So
Yes, sir.
okay, and I tried also in the say in the mall, no, not mall, hypermarket scenario, it works, right?
Okay.
Okay, so in a store for pedestrian, it works, but the for the real town, you need to tell. Okay,
So this is something we can add on to check
yeah.
if. Okay. Thank you, sir.
And a nice thing about this, yeah, imagine you have a new town,
Mm-hmm.
okay? So you build a new town that you don't even have the data, right? There is no town yet.
Yes,
You can
sir.
use IFN, isn't it?
Mm-hmm.
But you cannot
Actually,
use additional method because there is no OD.
yeah.
Yeah, there
Okay.
is no flow there. Correct. But using IFN, from the paperwork only, from the architect work or the urban planner work, which is just the number of lane, correct? You can already calculate, oh, this is the congested part. This is not congested. Okay. If we do
Yes.
this and that, you can actually improve it.
Mm-hmm.
And
Yeah.
one thing I want you to understand is this. What is the ideal of the idea?
Mm.
Okay. Because of the IFN that you don't need real data, okay, which is based on network topology, basically, isn't it? Okay. Now you can simulate network topology. Okay. And we discovered that already, yeah, several years ago. We discovered that okay, there are certain topology that actually better than the others. Wow,
Mm.
right? This is for the thesis, no? And then example, yeah, uh, when your network topology is actually pre-magic, you know,
Yes, sir.
pre-magic is the sum of row is the same as the sum of columns. Yeah? Your network topology, then the number of in decrease is the same as out decrease. So this is called in graph theory, this is called Euler network. Yeah? Euler network. So you can check also my video in YouTube about this. Yeah. So Euler network is actually one of the most ideal network
Mhm.
topologically.
Yes, sir.
And then you can also improve that. How about if your capacity matrix is already pre-magic? If your capacity matrix is already pre-magic, okay, then that is the most ideal. There is no more bottleneck.
Yeah. I
Okay.
think it's very useful for us, sir, especially if like on my experience as an architect, because
Hmm.
we do not really deal with a lot of real world data for traffic. And then
Hmm.
usually we are asked on how much uh
Hmm.
traffic it will attract,
Right.
which is
Right.
also very variable. So I think this method helps us to show or when getting permits to show that
Hmm.
how traffic will affect the the area without really having to go through extensive
Hmm.
counting, like you said. If the data is not there and it's a new development,
Right.
we can lessen the impact.
Now I want you to show, okay, prediction. Okay, so let's go to the long-term scenario in Moodle. Hmm, where is the? Okay, I will show you first. Maybe this one, policy analysis. No? Okay, so this one. Okay, in policy analysis, can you check policy analysis two? Okay, Can you see my slide?
Yes, sir.
Okay, this is very interesting. Okay, now you have the basic, yeah. Now we combine, okay, with your simple model regression. Yeah, now we combine IFN with regression. Okay, suppose you have this regression. Okay, let's predict, okay, where and when, which year, which month. Imagine that you can, using IFN, you can also predict where and when, okay, the traffic congestion will happen if you have a certain policy scenario. Okay. Look at this. If you use traditional method, you have this technique OD. Okay, you predict it. After you predict, there is no feedback whether your prediction is correct or not, isn't it?
Yes,
Right?
sir.
You will say, okay, I predicted, okay, I get this, and so on. The question is this correct or not? How you will say this is incorrect or not? So, but using IFN, you can predict. Based on this prediction, now you can check where actually and when.
Yes, sir.
So this is interesting, yeah. So let's see, okay. So if your model is correct, okay, then your prediction must be correct. Yeah. If your model is incorrect, then you get the feedback at least. Yeah. You improve your model, okay, to make it better. Is that okay? So let's do this. Yeah. The policy is simple. Okay. Instead of reduce, I will add lane. Yeah. I will add one lane, okay, in the most congested link when the maximum congestion is already exactly 0.9. This is the policy that we want to put. Okay. Remember, I just want to simulate, yeah, long-term prediction. Okay. There is no change in the network. Only the lane will change. The number of lane, yeah, will change. And then the capacity per lane, let's assume 1,500 vehicle per hour. Okay, let's say this is very small network, this is hypothetical. Okay, so the city's population, say in the year 2000, is 1,200 person, and the car population is 550 cars. Okay, so let's assume they are a growth of 5% per year. Okay, for the human, and then for the car population growth is 7% per year. Again, all this just number are make up, yeah. But now I get the total flow in the network, assuming in this regression model. Okay? Again, I just making it up. Okay? You can eventually create your own model, but at least it will give you idea. Okay, this is kappa. This is the total flow in the model. Remember, you can calibrate the kappa easily, right? If you know one link, you get the real data, you can get the kappa already. Remember that a while ago, yeah? So this is population, this is number of car. T here is the year. Okay, suppose this is the model. So this is our base scenario in the year 2000. Okay, so given this, so this is one lane, this is two lane, and so on. Okay, because 1,500, so one lane become 100, two lane become 3,000, and so on. Okay, so now we get kappa zero, that means year 2000. Okay, you just input that. Yeah? The population 1,200, population of the car by 550, right? You input in the regression, you get kappa 10,950 vehicle per, what's that? Vehicle per hour. Yeah, vehicle per hour. Okay. Now you get the maximum congestion based on that year 2000. Yeah, you get from this. You see here is 2, and then this is 1. That means you have 2/3, isn't it? Yeah, 2/3 and 1/3. This is the stochastic. You can easily compute. And then you can get the flow matrix based on this. And then you get the congestion matrix. Okay. Let's get the maximum congestion. Where? in DC, which is 0.61. Yeah, you can practice later. Yeah. So in the year 2000, okay, maximum congestion was 0.61, and we know where, which is in link DC. And then, okay, the question is when we will apply the policy, right? When it will reach the maximum congestion 0.9, right? Okay, so the threshold 0.9 will happen. Okay, you check because you have the regression model, you can check. Okay, 0.9 will happen when the total flow reach this one, yeah, 16,120. Yeah. From where you get 0.9, okay, you get 0.61. Okay, that is the global scaling. Okay, and then you multiply that global scaling with the current, yeah, in the year 2000, which is 10,050, you get 1600 16,200, right? And then if you know the total flow, yeah, and then you tabulate this, right? This regression model, you make tabulation, then you will know when it will happen. Yeah? You will know it will happen in the year 2009. Oh, you see, I know, okay, not only the link, which link it will have a maximum congestion, I also know when it will happen. If the policy is still this, 0.9, I will add one more link. Okay, and then based on that scenario 2009, now this is the flow and this is the maximum congestion, which is 0.9, right? Remember, the policy is when you have 0.9, you add one more lane in that lane. Okay, so in this case, DC, you add one more lane. Yeah. So DC now become 3 lane. Okay, because you change become 3 lane, what will happen? The stochastic matrix change, okay, the flow matrix change, and then now your congestion level change. You see here, okay, because you increase the number of lanes in DC, DC reduce, yeah, from 0.9 now becomes 0.6. Can you see that? Okay. In the same year, when you improve in link DC, okay, because of this improvement, there is congestion somewhere else. Where? In BC and in BE. Can you see that?
Yes, sir.
When you improve in one place, okay, the congestion is somewhere else. Using IFN, you know what is the impact of your improvement in here in other place.
Okay. So we can actually see the effect on the whole network, sir.
Correct. You see that. Okay. But when you are using traditional, what you are doing is just in one link only, isn't it? You're focusing in one link. No, we don't like that. We want to see the whole network. You are system thinking. Okay. You are not just in one place only local. You are doing it seems systemic. Okay. In the system.
We're not
Imagine that.
just transferring we're not just transferring the problem to other places.
Correct. Now, what will happen? Now we want to predict, okay, this is already close to 0.9, right? When it will happen become 0.9. Again, we use the same thing, okay, right? So, when it will become 0.9, oh, 0.9 divided by 0.82, isn't it? So, you have the scaling, multiply by that scaling with the total network, which is now become 1700,
Mhm.
17,780. Okay.
Mhm.
Go to that table a while ago, you will know that this is happening in 2011. Right, closer. You
Yes.
see?
It actually helps also, sir, in budget allocation. Like you will know
Correct.
where you're going to spend, what year you will need money for traffic
Yeah, if
improvements.
you use this policy, this is what will happen. You will see the long-term effect of the policy. Imagine that. Amazing, isn't it? So now I can continue until 2027. Okay. And at this point, okay, all link will be congested. Yeah, because it's already pretty much a capacity at this point. Yeah. So this is very nice. Using IFN, you are able to predict when, which year, and where, which link. Okay, based on certain policy scenario that you set beforehand. Okay. Of course, this policy scenario must be related to the performance of the network, which is in this case maximum congestion. You still don't like maximum congestion, you can use average speed or average travel time. That's fine. It's the same. The technique is the same. Right. So I hope with this you are more convinced. Okay, the usefulness of this method, right? So why this is important? Yeah. When you first you do system thinking now. Okay, you are not just dealing with local problem. Yeah, you are dealing with the whole network. Second, yeah, now you start to think long-term effect, isn't it? If I do this, what will happen in the future? Okay, then you start to prepare the budget. This is planning, isn't it? Yeah?
Yes, sir.
So
Ac-
exactly, this is
Actually,
exactly planning.
yeah, yeah. And we're supposed to check our policy within the short term, three
Exactly,
years, medium term, and long term.
right.
Check it already.
Okay. So you can start to see the whole thing, yeah. Okay. This is what is lacking in the traditional method. Again, why? Simply because you are going with OD matrix. This is the problem. Okay. Once you make it with OD matrix, well, now you need to predict the whole things, the population growth. Yeah, of course you do the same thing, right? Now, how to predict the OD? Again, you do a lot of models, yeah, right? Very complicated, right? You can do the same, okay, but at the same time, the more model that you put in, okay, especially this model are heuristic, right? So then you start to get confusion whether this is actually true or not. Okay, and then at the same time, when it happened, there is no feedback, right? Because you don't know where. You see, you just say, yeah, the average, the whole network average is like this. You don't check. How you check the whole network, right? The average the whole network is difficult. So because you don't check, so there is no feedback system. Because there is no feedback system, so your method is true or not, you don't know.
Mhm. And it's
Right.
reliant heavily on traffic count, sir, which is very expensive to ask people to do.
Correct. The also the budget problem, yeah, in collecting the data, right?
Yeah.
Okay. So in here, okay, yes, you still need traffic count, okay. At the same time, you can check, yeah, the traffic count is to verify, right, your prediction is correct or not. Okay, if your prediction is not correct, then you probably your regression model not correct, probably your IFN model not correct, probably your parameter in that not correct. So you can correct it, right? Improvement for the next one. Okay, with this, our system becoming better and better over time. Without feedback system, we never improve, right? So
Correct.
we get the feedback. How do you get feedback? Your prediction must be exactly the same as the reality. Okay? Using traditional method, there is no way you can get that. Right? How are you going to get the whole network average travel time, for example, in the year 2024? It's impossible because you cannot get the feedback system because you have no feedback system. You don't know whether your prediction is actually correct or not. You see? So, and then you rely on that and saying, oh, this one has been applied in this city and that city. Well, it has been applied doesn't mean it's correct because nobody ever checked about it, isn't it?
Yes, sir. And users have different behavior
Right.
for their use.
So using this, there is a tool that you can check. So if it is incorrect, you check because you know where already, isn't it? You know where and when, so you can actually check.
Yes,
Okay.
sir.
In the real field, no, you collect the data, you check. Oh, in this case, not correct. Okay, in that case, which part is not correct? Probably certain assumption is not correct. Right? So we improve it. Okay, this is science. Okay, we cannot just make it like wizard and say, okay, you believe me. No need to prove it. That's not true. Not
It
true
has to
science.
stand, yeah, it has to stand testing, sir. Right? Testing and
Oh, okay. So we keep improving. Okay, the theory is there, but you need to test it. Okay, and then you improve it again and again. Over time, you will see we are better.
yes, sir.
Okay, so I hope with this give you some idea. Okay, that you can actually use this technique. Okay. So okay, give me feedback, comment, discussion, question probably. Or you want to practice? Before I go to the next one.
I think, sir, we can go to the next one.
Are you sure?
Yeah, sir. If
Okay. So I call this ideal traffic assignment. Okay. I don't know if I put this already in the Moodle or not. If not, I can later put it. Okay. So you have a tool now. Okay. How to build a network tool, which is a traffic assignment. Okay. To analyze congestion in any city, right? So your budget is minimum to collect the data. Okay. Your budget to purchase the software is also minimum. This is free, right? So one more important things I want to introduce here is the possibility to connect it to ITS, Intelligent Transportation System. Okay, so using mobile trajectories using camera system, yeah. Okay, the motivation first, yeah. Ideal traffic flow, yeah, is used as guide to manage the actual traffic flow. Okay, so we are doing it in steady state solution. Remember, this is not based on, oh, at this hour or at this day. We don't calculate that, isn't it? In IFN, you calculate steady state solution. That means long-term solution. Okay, so that means ideal. That's why we call it ideal flow. Okay, so in that case, you have you will use this to guide, yeah, to manage the actual traffic flow. Okay, so you know the ideal, this is the goal, right? Then, okay, can we manage to improve our current situation toward that ideal, toward more uniformly distributed? So this is the goal. Last time in Ateneo, I give the computation on the premature capacity. That means the most ideal one. Okay, when I presented that to the board, they were shocked, yeah, because the number of change that we need to put is too much. So they said, okay, no need. Okay, this is enough. That is too much. Okay, so yes, it's okay. At least we know the direction. Okay, but what happened in traditional traffic assignment? Okay, you need the OD matrix, isn't it? And OD matrix is so expensive. I remember you have mutis, which is in 1996. Is that correct? And then MUSEP is 2016, isn't it? Right? So 20 years in apart, eh? Oh no. 20 years in apart. So why? Because it's very expensive, to do OD matrix survey. You can also have this problem. Yeah, how should the ideal flow in the network ideally distributed? Isn't it? The current technique is using Wardrobe principle. Yeah, which is either one, it is user equilibrium, it is NAS equilibrium, or social equilibrium. Yeah, Wardrobe principle two, which is minimize the system travel time. Okay, but look at this different way of thinking. Okay, what is the ideal condition? The ideal condition should be the most efficient utilization. Yeah, it may happen when the flow is actually in proportion, yeah, or distributed uniformly over the space and time. Okay, so if your network is without capacity, you will use uniform distribution. If your network is with capacity, you will use proportional distribution, right? You take the proportion of the capacity. Okay, and the most ideal capacity is actually pre-magic capacity. Okay, we know that. You can test it on your own, yeah. And then the most ideal network itself is actually Eulerian, I said earlier. So with this pre-magic number. So what is the meaning of maximum efficiency? You see here, this is the hour, 24 hour. This is the number of daily traffic, right? The peak hour in the morning and peak hour in the evening. Okay, our goal is to flatten this. The same thing here. See, this is in terms of time, yeah? In terms of space, you see, because you are using only home base technique, right? So you see now your network is something like this, highly inefficient. Half of the network is fully utilized. Half of the other network, the other direction is not fully utilized. Empty, almost empty. Right? So in this case, you are not using it efficiently. That's why I introduced redistribution of congestion, you see. Yeah, you try to redistribute the congestion so that they will use other links, not only in this link. Okay, so of course, in the context, yeah, we have demand and supply, right? The supply means you have the infrastructure, the connectivity, the capacity, right? You have the demand, which is the flow and the OD flow, and then you have the performance between the demand and supply, which is in terms of speed, maximum congestion, delay, and so on. Yeah. So how do you compare? Yeah, you compare these indices. Yeah, and when you do what is called traffic assignment, what is traffic assignment? Traffic assignment basically assign the traffic flow into the network, right? So what is traffic flow? Traffic flow is basically the aggregated or the count of the trajectory of each agent. Okay, look at the basic idea. Okay? You have agent, which is the vehicles or the people, okay, passing through the network. Okay, they are creating trajectory over time. Okay, and then this agent that create the trajectory over time, when you aggregate them, we call this traffic flow. Okay, so in the traditional traffic assignment, you have OD matrix, yeah, you have road network with the length and the capacity and the maximum speed, of course, and then your output is the flow on the network. Yeah, using IFN, you have the capacity restraint, which is also all or nothing. It's the same as traditional traffic assignment. Okay. So, and then what is the problem with the traditional technique? To obtain OD matrix, yeah, what you will do? The real OD matrix, you need to do license plate matching. Okay. Ateneo alone, at that time, we do a license plate matching. We need 200 people in 2 days. Yeah. So the total cost is like 1 million pesos just for Ateneo alone.
Expensive. I don't think we
Super.
can have a client who is willing to pay 1 million just for the traffic data, sir.
Government. Right. Okay. So you can also use color card distribution, right? So when the card, say you cordon the area, right? And then you give card, okay? They are coming from this place. Okay, they give you give the card, and then when they go out, you take back the card. Okay, so you will know O and D, yeah? Origin and destination. Right? And another idea is to use household interview, isn't it? So from here you can estimate the traffic flow. Yeah. So the new method, okay, is to use GPS, of course. Yeah, using a mobile phone, right? So using GPS, you get trajectory data, isn't it? And then you can get the OD matrix. Okay, and from there you collect the data and then you do a lot of data analysis. Yeah. Now using FN, okay, you have the steady state condition. You can choose with or without OD flow. Okay, without is actually easier, right? With OD flow, you will convert that into a turning probability in each intersection, right? And then do the traffic assignment as usual. You can also choose with or without the traffic flow, yeah, not just OD flow. You also have a real flow a while ago that you can input, yeah. And then these are the basis. Yeah? The basis is actually probability distribution, and then random walk and Markov chain. Yeah? These are the mathematics behind. Okay, so look at this so that you can compare. Yeah? The traditional method, you have OD matrix, you have the network, and then you do route choice, right? The shortest path, isn't it? Yeah. And then you go that route choice inside based on that OD matrix, and then you get the flow. Okay. Now these three, the OD matrix, the network, and the route choice, okay, when you combine them, it's actually the same as stochastic matrix. You aggregate them. So in a sense, okay, ideal flow traffic assignment is simple from stochastic matrix to the flow, okay, which is basically the same as traditional, but you already have the OD matrix inside. Okay, how can you have inside? Well, that probability in each intersection, remember, in each intersection you have probability to turn left, to turn right, and so on. That one is much more than the OD matrix zone base, isn't it? Say the whole Metro Manila, you probably have only 100 zone or 200 zones. But how many nodes in Metro Manila? More than 1 million.
Sure.
Right? So that means you have more data. If you put, say, camera in each intersection in this 1 million nodes, that's impossible, isn't it?
Yes, sir.
Right. So in that case, how we will approximate, okay, okay, that is the one that we put as proportional. Okay, that's why we take the ratio of the road capacity. Okay, or the road width, the ratio of the road lane, the number of lane, or the road width. Okay, basically the capacity, right? So when you take the proportion of the capacity, this is an approximation. Okay, not the true one, but why we need approximation? Otherwise, you need to get the data, the stochastic matrix, okay, for all these intersections in the whole city. more than 1 million. It is impossible. Okay, so we don't say that, oh, using IFN, we don't need data. Well, it's true because you assume something. Remember that, okay? Very big assumption here, okay? That you
But we
take
can,
proportion.
sir.
Yes, yes.
Yeah, sir. But we can take real world data to strengthen our argument for IFN.
Correct. Exactly, that is what is called maximum entropy principle. Okay? When you have maximum entropy principle, what is the meaning? In maximum entropy, okay, we are telling this. If you don't have data, assume uniform. If you have data, assume based on that data. Okay? The more data that you have, the more accurate you have result. The less data that you have, you can still do. This is the most important part. You can still compute even without data. Why? Because you assume something. Okay. You want to get the idea of maximum entropy before I go? Oh, okay. Let's go back. Let's go to maximum entropy later. Yeah. Here, uh, ITS first. Okay. Now, what happens if you have real data? Say you have several cameras, okay, and then you have a mobile data that connected to your database engine. Yeah. So you have probe card, you have camera in the intersection. All of these data that you can combine them into one real-time update. Okay. Say instead of using proportional capacity, now your stochastic matrix in that particular intersection you change based on that real-time update. Okay. When you know the flow, the real flow, you update that flow. Don't use proportional capacity. Use the real time. Because data is the ground truth. Remember, if you don't have data, you assume. But if you have data, use that data as ground truth. This is very important, right? So that you will get the actual real time. Then your IFN now become real time. You can create navigation system like Google Map based on IFN. Okay, maybe this is your next project. I don't know. Yeah. Okay, at least this is the idea. Okay, so okay, this is the one that you already know. Okay, so let's go to Excel so that I will introduce you to. Can you see my Excel?
Not yet, sir.
Not yet. Okay, I will create a new sheet here in Excel. You can also do the same. Okay. Say I have A, B, C, D, E, F. Okay. Put any number you like. Say I put 20 here. Oh, any number? What number you like? What is the lotto tonight? 27?
27, sir.
Okay, 27 to 43. Okay. So I will have 13 here and 17. And let's make it 52. Okay. So these are my number. Okay, put here, and then I will put sum in here. Okay, I will put sum here. I will put total here. Okay, I can put standard deviation if you want. STD. So sum. Okay, sum of my data. Okay, this is my data. Okay, of course you will. Oh, the total. Sorry, average. Average. Yeah. So the average is the average, right, of my data here. Okay, and now we have standard deviation. You want, okay, maybe complicated, but anyway, as the def, right? Okay, make it population. Okay, so these are the value. I will copy here as value. Okay, copy as value. So suppose you know this data. Okay, and from the data you get the statistic. This is called statistics, isn't it? Sum, okay, average, standard deviation. These are all statistics. Yeah. So I will put here. This is called statistic. Yeah, statistics. Okay. So from data you get the statistics. Yeah. Now what happen if one of your data is don't know? What will happen if you don't know this data in F? What will happen? Okay, you calculate, okay, and you have 120, right? And this is, earlier you know, this is supposed to be 172, right? Right, okay. This is supposed to be 172, but yeah, this is the sum. I'll put a color here. This is the correct one, the 172, but you now get 120. So what is the value here? Of course, you will say that one is 172 minus 120, isn't it? Correct? If I put 52 here, oh, there I get it back, right? So if I have missing data, only one, I can get back, correct?
Yes,
Yeah.
sir.
If I have this, I have missing data, and only one data, I can get back. Okay. Now what happens if I have two missing data? What is the value in E and what is the value in F? Give me. You have two missing data here. Oh, you said, okay, in that case, I will do the same. 172 minus the sum, okay? Oh, 69. Can I put 69 here and then I put 0 here?
No.
Yes, you can get the sum, but the standard, your standard deviation is not the same, isn't it? Right?
What do you
Well,
do?
no, it's okay. Yeah, you can put any value, isn't it? I can put 71 here, and then I can put minus 2 here, right? I will get exactly the same 172 again, right? So if you have missing data and you don't know, what you will do? You assume. Remember, yeah, you assume. You assume equal, yeah, distribution, yeah, uniform distribution. So in that case, I will have 69 divided by 2. Oh, what happened this? Oh, sorry. Okay, I will put 69 here. 69 divided by 2. 69 divided by 2. Okay. And then again 69 divided by 2. Oops. Equals 69 divided by 2. Okay. Yeah. The standard deviation not the same. Okay. But the sum is the same. The same thing if you have a 3 missing value, what you will have? You minus this, right? Minus the sum. And then now you divide by, sorry, I need to delete this too. So now I have 3 missing values. Okay. What I will have here now become 82 divided by 3, isn't it? So if you have a missing value, okay, you assume equal distribution. Can I not doing that? Can I doing something else? Yes, you can. But when you, for example, I put 30 here, if I have 27 here, and then now I have how much? 25, right? So when you do like this, what will happen? That means you already assume something. You already assume certain probability distribution which you don't have any basis. Right. You don't have basis to say that this is 30, this is 27, and this is 25. What is the basis? No basis. But when you said, when I divide equally, what is my basis? Your basis is actually maximum entropy. Oh, how can it maximum entropy? Oh, let's do this. Huh? So I will show you. Okay. So let's calculate the probability. Probability. Okay. So what is probability? This one divided by the sum, isn't it? Okay. So this sum must be the same. So I need to put with the dollar sign. Okay. So I compute this. At this point, I have 0, 0 at this point, probability. Okay. So I make colorful so that you saw. Now, after that, I can calculate the entropy part. Entropy part. Okay. Entropy is simple. Okay. So, which is equal to probability multiplied by ln of the same probability. And then you sum. But this is always negative, so you put negative value here. Right? And then if the probability is 0, you put it 0. Look at this. If I put 0, it will not become a number. So in that case, I will put if error, then 0, so that it becomes 0 if the probability is 0. Okay, now what is the entropy? Entropy is just the sum of the entropy part, right? So the sum of this entropy part. Now I have this entropy. So now let's do solver. Okay, let's do solver. What I will do, I want to maximize this D10 with this entropy. I want to maximize, okay, by changing cell. What do you want to change? This one, right? I want to change this one. Okay, subject to constraint. Okay, what is the constraint? This sum must be the same as this one, right? And so there I found the solution. Wow! You see, maximum entropy give you exactly uniform distribution. Right? Now you have the basis, So you optimize, okay? When you said, oh, I do maximum entropy, you are actually doing it, with certain assumption, which is to optimize something, in this case, you optimize the entropy. Entropy is starting from physics, It's for thermodynamics, right? So you probably learned it in high school, entropy, thermodynamic too.
Decades ago, sir.
Yeah. Right, right. So, but at least you give you get the idea, that uh, the more data that you have, that means you have no missing value, right?
Yes, sir.
You can get better result, more accurate result, in terms of standard deviation and so on. But if you don't have it, you can still use maximum entropy, which is exactly the same as IFN, right? It is
Yes,
based
sir.
on maximum entropy, to compute that, in order to get the value, even though you don't have data. So
Um, it
yes,
actually it gives us a mathematical basis for our
correct,
estimate, which makes
correct.
it more sound than just throwing random numbers in.
Yes. So remember in modeling, yeah, the whole idea of modeling is very flexible, especially with mathematics. Yeah, you can model anything. Okay, as long as you know what is your assumption, you know what you're doing, right? Okay, you know the assumption, you know the invariance. Okay, you state it, and then people can do it the same. We get the same result. Okay. Okay, if the model is incorrect, so make it correct. So we improve it. Okay, if it's not accurate enough, so you make better model, no problem. Okay, so with that you can predict, you can control. Okay, you can understand the phenomenon. Remember the earlier classes, no? In introduction to modeling. Okay, I hope with this give you the idea. Okay, so in January. Okay, so you will have a project presentation. So I hope you finish it by January. Okay,
We'll just
and
email you in case we have any queries, sir.
yes, so you can ask anytime, yeah, by email.
Okay.
Okay. And thank you very much for today.
Yes, sir.
Okay.
Thank you all. Sir.
Thank you, sir.
Thank you, sir.
Yes.
Thank you, Prof.
Happy holidays, sir.
Oh yeah, Merry Christmas and Happy Holiday.
Everyone.